Hi, my name is Atika and I will explain part 1, which is process state and transitions. So figure 1 shows the different state a process goes through during its lifetime and the transition between these states. A process can be in one of 5 states, which is new, ready, running, waiting, and terminated. This state depends on how the operating system schedules the process and handles event. First, a process enters the new state. This occurs when a new process is created to execute a program. At this stage, the process is being initialized and prepared to enter the system. Next is the transition from new to ready. The operating system moves the process into the ready state once it has allocated the required resources and the system is prepared to handle an additional process. In this state, the process is ready to run but is waiting for CPU time. The process then moves from ready to running. This happens when the CPU scheduler selects one process from the ready queue and the dispatcher assigns it to the CPU. At this point, the process begins executing instruction. While in the running state, the process may be interrupted. If it reaches its maximum allowed execution time, the operating system preempts it and moves it from running back to ready, allowing other processes to execute. Another possibility is that the process requires an event such as input or output operation. In this case, it transitions from running to waiting. The process remains blocked until the request event is completed. Once the event occurs, the process moves from waiting back to ready, making it eligible for CPU scheduling again. When a process completes its execution or is forced to stop due to an error, it transitions from running to terminated. The operating system then releases all resources allocated to the process. Sometimes a process can also be terminated directly from ready or waiting if its parent process ended. So in conclusion, this state transition allows the operating system to efficiently manage multiple processes and ensure best CPU utilization.
For this slide, we implement the first come first served scheduling algorithm. Based on Gantt chart, we can see that processes are executed strictly according to their arrival time, starting from P1 until P8 without any interruption. This means once a process starts, it must finish before the next process can run. From the output shown, the waiting time and turnaround time are calculated sequentially for each process. As you can see, some processes are experience longer waiting time because they need to wait for earlier processes to complete. This shows that first come first serve is simple but not efficient when short processes arrive later. This coding implements the first come first served scheduling algorithm. Processes are executed based on their arrival time, meaning the first process that arrives will be executed first. In the code, the arrival time is stored in the add array and the burst time is stored in the BT array. The variable CT is used to track the current time. For each process, the program calculates the turnaround time and waiting time. At the end, the average waiting time and average turnaround time are displayed. This algorithm is simple, but it may cause long waiting time for short process. This slide shows the shortest job first scheduling algorithm. Referring to Gantt chart, the process with the shortest burst time is executed first among the available processes. This causes the execution order to be different compared to first come first serve. From the output, we can observe that the waiting time for shorter processes is reduced. As a result, the average waiting time and turnaround time are lower compared to first come first serve. However, short job first requires more decision making because the system must always choose the shortest job. This coding represents the shortest job first scheduling algorithm. In this algorithm, the process with the shortest burst time is selected first. As long as it has already arrived, the array D is used to mark whether a process is already completed or not. The program continuously checks for the shortest available job and executes it. Waiting time and turnaround time are calculated after each process finishes, compared to first come first serve. Short job first usually give a lower average waiting time, but it is more complex to implement. For this slide, we use the round-robin scheduling algorithm with a time quantum of 4. Based on the Gantt chart, each process is given a maximum of 4 time units before the CPU switches to the next process. This allows processes to run in cyclic order instead of finishing in one turn. From the output, waiting time and turnaround time are calculated after all processes complete. This algorithm improves fairness because all processes get a chance to execute. It is commonly used in time-sharing systems. This coding demonstrates the round-robin scheduling algorithm with a time quantum of 4. Each process is allowed to run for a maximum 4 time units before being switched to the next process. The array R stores the remaining burst time for each process. The variable T keeps track of the current time. If a process finishes, its completion time is safe. This algorithm improves fairness because all processes get CPU time, especially in time-sharing system. This slide also used the round-robin algorithm, but with a smaller time quantum of 2. From the Gantt chart, we can see more frequent context switching compared to quantum 4. This makes the system more responsive, especially for short processes. However, it also increases overhead due to frequent switching. From the output, we can compare the waiting time and turnaround time with quantum 4 to see the impact of using a smaller quantum. This coding is similar to the previous round-robin algorithm, but the time quantum is reduced to 2. With a smaller quantum, context switching happens more frequently. This makes the system more responsive, but it also increases overhead. Waiting time and turnaround time are calculated in the same way as before. By comparing quantum 2 and quantum 4, we can see how the time quantum affects system performance.
Hello, my name is Nisa Ismahani. On this slide, I would like to talk about the best performance scheduling algorithm. Based on this comparison, the shortest job first gives the lowest average waiting time and turnaround time. This is because shorter processes are executed first. Compared to that, first come first serve is not efficient when long processes come early. Round robin also increase waiting time because of frequent content switching. So overall, shortest job first is the most efficient for this process set. This slide will explain the impact of scheduling algorithm on system performance. Scheduling algorithm affect waiting time, turnaround time, and response time. First come first serve is simple but not efficient when process lengths are mixed. Shortest job first improve efficiency but need no burst time. Round robin improve fairness and responsiveness. So, the choice of algorithms depends on system type and workload. Now, let's look at the strengths and weaknesses of scheduling algorithms. First, first come first serve is easy to implement and fair, but it can cause long waiting time. Next, shortest job first give the best average waiting time, but it may can cause long processes to wait too long. Lastly, round robin is good for interactive system, but if the time quantum is too small, it can cause too much context switching. So each algorithm has its own advantage and disadvantage. In conclusion, different process scheduling algorithms affect system performance in different ways. Based on our analysis, shortest job first gives the best performance because it results in the lowest average waiting time and turnaround time. First come first serve is easy to implement, but it doesn't not perform well when long processes arrive early. Round robin provides fairness and good response time, but its performance depends on the chosen time quantum and may cause extra overhead due to context switching. Therefore, the choice of scheduling algorithms should depend on system requirement, workload type, and performance priorities. Thank you.